Solve probability problems, you can have different diagrams. So one of them is called a Venn diagram. I believe you've seen these all before. So it's basically two circles that overlap. You can have three and you can have more than that, but it's unusual. So usually we're dealing with two events, let's say event A and event B, and it looks like this. The box is the universal set. So everything must be contained within this box. So if it's the probabilities that you're writing down, you would have to have a total, everything in there to add up to one. Okay. If it's the items that you're listing, then your box, your Venn diagram would have to total up to the total number of things that you're counting. So if I take an example here, usual number one here, a survey of 117 consumers found that 81 had tablet computers, 70 had smartphone, and 29 had both smartphone and a tablet computer. So there seems to be dealing with two things, smartphone and tablet computers. So if you want the diagram, you could try to calculate this without, but let's go with it. So for this one, I'm just going to reuse the one I got here. So for this one, let's give some nice letters. So tablet and smartphone. You always start, if you're drawing these, it's best to start with the middle part, the part that overlaps. This part here is where both conditions are true. And in this case, they give it to you. 29 had both. So 29 would go here. Sorry, it's so small. And 70 had a smartphone. Now the trick is here, the 70 doesn't go here. This is wrong, because if you look at this, if you add up everyone that has a smartphone, there's 90. I've written down 99 of them. It just happens that out of those 99, 29 of them also have a tablet, and it doesn't say that in the question. It says that 70 had a smartphone. Now, it doesn't say that's all they had. So let me be careful here. Yeah, it doesn't say they only had a smartphone. They say they had a smartphone. So this would be wrong. But if 70 of them have a smartphone, this would leave me with 41 here. 41 only have a smartphone. 29 of them have a smartphone and a tablet, which adds up to 70 having a smartphone. And then 181 had tablets. So same deal there. 81, so that would be 52 only have tablets. 29 have tablets and smartphones. So that adds up to 81 people in total. Now, if I add those up, I got 52 plus 29 plus 41. That's equal to, I'm just that lazy right now, I'm going to use a calculator, 122. And they say there's 117. What did I calculate wrong here? That's not possible. 70 had a smartphone. 81 had a tablet. Anybody see the mistake? Please tell me. Because my numbers don't add up. I'm exceeding the number of people that have been surveyed. So 81 had a tablet, 70 had a smartphone, 29 had both. Okay, that's an impossible question. The idea was that it's possible that there's nobody some people don't have either, and that would have gone here. Well, that's annoying. Stupid question. Let's try another one. This one looks longer. Class of 20 students, 12 study biology, 15 study history, 2 students study neither biology nor history. Okay. Let's see here. So for that one, this is number 2. History, biology, and then they do say, I don't know how many have both, but I do know that 2 students study neither of that. Very wise people. So 2 go here because they're not inside of H or B. So that leaves me with 18. So the 3 spots inside, this one, and this one, has to add up to 18. Now, if I just write down 12 in biology and 15 in history, that would add up to 27, far exceeding 18. So the way to think about it is the history folks, I'm going to give you a formula here that's going to come up shortly. Wow, they really, the book really does things in reverse. What we call that is, this would be history and biology people. That's not hub, that's kind of a big U, but it's history union. That's a symbol for union. So it's history and biology, we would say in English. So there's 18 people that are in history, or biology, or both. And there's a nice little formula for that. This is history union biology would be equal to the history folks plus the biology folks. But the problem is there's some that are in both, so I've kind of double counted those who were in both. So I got to subtract them out. So there's a new symbol for you here. This one is called an intersection. And this would be and. This one, you kind of say it in English, sorry, I should correct myself, that's or. So it's you're in history or you're in biology, but it also means you can be in both. So I think the best way to say it, and there's no great way in English to say it, is it's an and or. Okay? So it means that you can be in history, the union, or biology, or both. The intersection means you have to be in both. And so this one would be, the way to calculate it, I guess they're expecting you to just figure that out, is 18 is equal to 12 in biology, 15 in history. 15 plus 12 minus the intersection. What it allows me to do is figure out the intersection. So it's 18 equals 27 minus H intersect B. So H intersect B is equal to 27 minus 18, which is equal to 9. So there's 9 people here. That means that there are, in history, there were, how many? 15. So there's got to be 6 here that only take history. That adds up to 15. And in biology, there were 12. So there's got to be 3 here that only take biology. And if you add all these numbers up, it should add up to 20 because there's 20 people in total. And that's true. So you can check your work. Okay? So to recap that, if you're drawing these things, A, B, there's this zone, there's this zone, and then there's this zone, and then there's, I don't know, this zone. Sorry, I forgot to color code them. Yeah, they're your 4 zones. Now, if you're looking at notation, this one, let's start with the easiest one. This one is A and B. It has to fulfill both conditions to be in there. And this one is, the yellow is fairly easy too. It's anything that's inside of A or B, but not. Okay? These 3 here all added up would be A union B. So it's everything outside of that. Another way to write that one, by the way, is it has to be outside of A and it has to be outside of B. So that's another way of writing it. The purple one, it would have to be inside of B and outside of A. And this one, the green one, would have to be inside of A and it would have to be outside of B. There, nice little ways to calculate that. So I wrote it down as probabilities, but like I showed you in the problem above, it could just be number counts of things, like in this one. It could just be the number count. Yeah, that's Venn diagrams. Sample space is you make a little table listing off everything. So if I look at this one, it's not used that often, but you can almost visualize them because usually they just stick to dice, 6-sided dice, or dice and flipping coins, or some variation where it's fairly straightforward. So this one, for example, in number 1, a fair cubical die numbered with the first 6 prime numbers. Okay, that's a little different. He throws his die, fair cubical die numbered with the first. He throws his die and a fair tetrahedral 4-sided die numbered with the first 4 square numbers and writes down the difference between the 2 numbers. Oh my goodness, they've gone mad. Okay, so what you do is you make a table. So on one column, you put in one of the events, and on the other, you put the other events. So a 6-sided die with the first 6 prime numbers. So 2, 3, 5, 7, 11, 13. Those are the first 6 prime numbers. And the other dice is 4-sided, and it has the first 4 square numbers. I think 1 counts. So 1 squared is 1, 4, I think this is what they mean, 9, and 16. Those are the first 4 square numbers. And writes down the difference between the 2 numbers. And I guess it doesn't matter which one you're subtracting first. So what you can do is you're making basically a little table. Goodness gracious, they have to make it complicated. So the difference between these 2 numbers is 1, this one is 2, this one is 4, this one is 6, this one is 10, this one's 12. 4, so that's 2, and I know it could be negative, but I'm just going to leave that alone. The difference in these are 1, 1, 3, 7, and 9. And the difference in this one is 7, 6, 4, 2, 2, 4. And 16 is, let's see here, 14, 13, 11, 9, 5, 3. Okay, so this section here is what your difference is between the 2 numbers. There you go. So what do they want to know? They want to know what are the chances that it's a prime number. So let's highlight those orange or something like that. So prime numbers, let's see, you got 1 here, 1 here. Got 1 here, 1 here. Got a prime number there. Prime number, prime number. Prime, 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 think I got them all. So the probability that it's a prime is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11 of those orange dots out of 24. 24 dots in total, or outcomes in total. Doesn't matter if some repeat, that really doesn't matter. So there you go. That's A, and B, a square number. So probability that it's a square number. Let's change that up. Let's go with blue. A square number. I think 1 is a square. I'm going to go with it. That's it, I think. So 2, 4, 6, 8. So it'll be 8 out of 24. Okay, so things like this. I'm not going to do it, but this one looks interesting because it's a genetic material and it's got a little chromosome puzzle there. That'd be a neat one to do. I think these are more of the same. And I'm just not that into it. You can play with it. That's fine with me. I'm going to stop here because we'll get back to other types of diagrams and also some more details on notation there.